In this example, we're going to look at another case of using the Biot-Savart law to calculate the B field at a point in space. And right off the bat, please get into your notes that this solution we're going to look at is a bit messy mathematically. You do not want to memorize the details, and the result of what we're going to do here will be given if needed. What we are looking at is a section of wire, so not necessarily an infinitely long wire, but a section of wire that is going to go from point A to point B, and we're looking at calculating the magnetic field B above the wire at some point Y above the wire. And it can be anywhere above the wire. It does not have to be at the symmetric, geometric kind of center of the wire. It could be offset. I could move the point over here, way over here if I wanted, right? And our result will certainly change the angles theta 1 and theta 2 that we have listed here. But the general result will apply anywhere as long as it's over top of the wire. So let me erase some of this. Okay. And what we are looking at doing is, again, using the Biot-Savart law. So what we are going to do is take a look at applying the Biot-Savart law to the IDLs. So the IDLs that are part of the current flowing in the problem. And I have an IDL here, and then as we pass the point right underneath the B field, we have more IDLs out here. And what I am going to show you, and the IDL becomes an IDX because this is one-dimensional, and what I'm going to show you is that we are going to solve the problem for the right-hand side only. So from 0 to point B, so the right-hand side only. And then the mathematics to solve the left-hand side would be the same, but we're just going to have to then replace the theta 1 with a theta 2. So let's do it. So we have the cross product. If we do right-hand side only, IDL, right, IDX cross R hat, where R hat goes from the IDL to the point in space where we want to calculate the B field. That would be IDL cross R hat. That's a thumb out of the paper. So the B field is coming out of the paper right away. So we know the B field is coming out of the paper. Well, the IDL cross R hat. Well, the cross product is the angle, the sign of the angle, between the two vectors drawn from a common origin. And notice that angle phi is going to be changing as we do our integration from right underneath the wire till the end of the wire B. So that has to stay in the integral. The x-coordinate is changing as we go from 0 to point B, so that stays in the integral. So that's in, that's in. The r goes from the IDL to the point in space. That is going to be changing. That stays in the integral. And then we can bring out the mu naught, the I, and the 4 pi. So these come out, and the blue ones stay in. So at the very least, in terms of what you would be responsible for, right? You're not going to be responsible for all the math, but I would say you definitely should be able to set up the problem to this point. Okay? Now, what we are going to do to be able to integrate this integral is some mathematics in here that you definitely do not need to memorize. It turns out it becomes convenient to be able to solve this integral by taking that sine of phi and replacing it with cosine theta 1, and I have the math for that shown here. So basically, we have that phi and alpha equal 180 degrees, theta 1 and alpha equal 90 degrees. So, and we're using the trigonometric relationship between sine and cosine to show that sine phi equals cosine theta 1. So, check. Again, you would only know to do this by sitting and attempting to solve it and realizing that the x coordinate from 0 to where the IDL is and the y is equal to tangent theta. When we solve that for x equals y tan theta. If we take the derivative, dx d theta, we would get y secant squared theta, so dx equals y secant squared theta d theta. So we are going to substitute that in, but before we do that, we're going to replace secant theta with r over y, so our dx becomes y r squared on y d theta. And now we get a lot of simplification that we are only integrating with respect to cosine theta. Again, don't worry about trying to memorize all of this. The result, when we do the integration, is to get that we have mu naught on 4 pi, 1 on y sine theta. And as I said, by symmetry, the left-hand side will behave the same, but we have theta too. So this equation to get b at some distance above the wire for the finite wire will be given to you if you need it. But for right now, we are just going to use it to analyze what would happen if instead of a finite wire, we had an infinitely long wire. Well, if we go from a finite wire to an infinitely long wire, both of these theta 1s and theta 2s, the max, by the way, is the distance. Theta 2 max would be based on right to point A, so that's theta 2 max. Theta 1 max goes out to point B, so when you're integrating with respect to theta, you'd be integrating with respect to 0 to theta max. But as the wire becomes infinitely long, so as we begin to stretch this wire to the right, that theta max begins to get closer and closer to 90 degrees until at infinity it equals 90 degrees. So that is why theta 1 and theta 2 equal 90 degrees for an infinitely long wire. When they go to 90 degrees, sine of 90 degrees is 1, sine of 90 degrees is 1. That's where the 2 comes from. The 2 cancels out with the 4 on the bottom. So what we get is that the B field outside of a long straight wire is mu naught I on 2 pi y, and if we consider that y to be a radial distance away, because we know that the current makes circular B fields around the wires, notice that for a long straight wire, we get that the B field goes with 1 on r, whereas in the Biot-Savart law, for each IDL, we saw that the B field, not on 4 pi IDL cross r hat over r squared, it was a 1 on r squared dependence only for one IDL. But when we have an infinite number of these IDLs, they sum together to have the B field drop off according to 1 on r, not 1 on r squared. And remember we said that B fields make circles around wires. So notice we have our 2 pi r circle in our answer. And as we were just saying, that the B field decreases as 1 on r, not as 1 on r squared. So the other thing to notice here is you can use this curl rule to get the direction of the B field. Now, for problem solving, you'll see that I will almost always go right to IDL cross r hat to get this specific B field region at any point in space. But just as a kind of quick and dirty way to say, well, what's the B field doing around a wire? If you let your thumb become the current for the wire, then you can make your right-hand thumb The current, as they show here, spin your fingers, and then your spinning fingers becomes the B field direction. So we're going to do more with the long straight wire, so we have our result that the Biot-Savart law can be used to calculate the B field for a finite wire. Don't have to memorize that. Is going to be extended to the infinite wire, and this one we will be memorizing simply because we're going to be using it so much that for an infinitely long wire, the B field is mu naught I on 2 pi r. And we'll do some homework. We'll talk more about this in class, and we're moving along.